Hello, my name is Amaika Chavez, and this is my multivariable function presentation. My presentation overview, basically the function I chose was number 18, which is fxyz equals x squared plus y squared minus z squared over the domain x squared plus y squared less than equal to 4 and z being between -1 and 1. So for the whole presentation overview, there's 4 parts I went over. The first one being domain and surface behavior, partial derivatives and critical points, applications of vector calculus, and the triple integrals. The first part is going over the domain and surface behavior, basically plotting the function. And for this, I use Desmos, the 3D graph. So this was the graph I ended up getting, and the graph it displayed. So for the domain, the inequality represents a circular cylinder in the xy plane with radius 2, and the constraint -1 at 1 limits for z limits the domain vertically to an infinite height along the z-axis. And for the range, the minimum occurs when x squared plus y squared equals to 0 and z2 equals to 1, giving the minimum equal to -1. The maximum occurs when x squared plus y squared equals to 4 and when z squared equals 0, giving f maximum equals to 4. So therefore the range is from -1 and 4. For the surface shape and behavior, the shape describes a hyperboloid of one sheet because it can be rewritten as x squared plus y squared equals z squared. For the symmetry, the function is symmetric in x about z equals to 0 because -z equals to 2, or -z2 is even. For the boundedness, the surface is bounded by a cylinder and 2 planes due to the constraints on x squared plus y squared equals to and z. For the asymptotic behavior, it is within the given domain. There are no asymptotes as the surface is bounded. And then for the graphing, the 3D plot will show a saddle-like surface bounded within a cylindrical domain. For the level curves, contour lines will be ellipses when viewed from above, varying based on the constant f, the function f x y z equals to c. For the second part, I went over the partial derivatives and critical points. This part, I did the equations right here. And then for the first order partial derivatives, the first one over x is equals to 2x, for y equals to 2y, and for z equals to -2z. For the second order partial derivatives, we got the values 2, 2, -2, and then 0. For the critical points, setting the first order derivatives to 0, we get 0, 0, and 0 for all of them. And then I went ahead and did the second derivative test. This was the equation for d. And then since d is less than 0, the critical points, all 0 is a saddle point, which confirms what we got for the 3D graph as well. The classification for the partial derivatives and critical points, there are no local maximum or minima within the domain. The critical point equals to 0, 0, 0 and is classified as a saddle point. For the third part, it went over applications of vector calculus. So basically found the gradient vector field, the steepest ascent and descent, and then did the Lagrange multipliers for constrained extrema. For the gradient vector field, we got this and then computed the partial derivatives to get these values. And for the steepest ascent and descent, the gradient vector of f points in the direction of the steepest increase of the function. The steepest descent, the negative of the gradient function, points in the direction of the steepest decrease. The interpretation basically was at any point x0, y0, and z0, the gradient 2x0 to y0 and negative 2z0 describes the rate and direction of change of function x, y, z. Then on this part, went ahead and did the Lagrange multipliers for the extrema and got these values. For x and y, the equation simplified to x squared plus y squared equals 4 and a circle of radius 2 in the xy plane. For the constrained extrema, critical points are on the circle x2 plus y2 equals 4 and z equals to 0. We evaluated the function xyz and it representative points on the boundary. And then for this part, went over the triple integrals of the function over the domain and triple integrals for the given function. And then I set up and evaluate a triple integral over the domain. This domain represents a cylinder in x squared plus y squared less than equal to 4, meaning the radius 2, capped between z equals -1 and z equals 1, the range. And then here I went ahead and did the work on a separate sheet to find the volume. This was the domain transformed into this equation, the height, and then here I went ahead and did the triple integral. And then this part was for the inner integral, the middle integral, and then the outer integral was just the value obtained from the middle integral multiplied by the integral 0 to pi over 1 d theta, which just equals to 2 pi. Once multiplied, we got the volume 992 pi over 45. And then for the conclusion, in this project, we explored the multivariable function of f x, y, z equals x squared plus y squared minus z squared and analyze its properties within the domain x squared plus y squared less than equal to 4 and -1 less than equal to z less than equal to 1. Then we identified the domain, range, and symmetry of the surface, visualized its behaviors using contour plots and 3D graphs, which is what I did here, and classify the critical point at 0, 0, 0 as a saddle point. Then using vector calculus, we computed the gradient to understand the directions of steepest ascent and descent and applied the method of Lagrange multipliers to find constrained extrema. Then finally, we evaluated a triple integral to determine the enclosed volume, illustrating the function's geometric significance within its bounds. And that was it.